Hello, this is Meteorology 113, Lecture 11, Local Scale Air Pollution and Air Toxics. This is the first lecture of course Module 5, Local and Indoor Air Pollution. We begin with an overview of this course module, the concluding one for this course. It comprises two lectures. The first, Lecture 11, is on local air pollution and air toxics, which we will proceed with shortly. The second is on indoor air pollution. The theme of the module and the lecture topics that comprise it is to learn about air pollution problems that affect more at an individual neighborhood scale rather than over a larger population. This distinction between individual versus population scale will become more clear as we proceed with the material. However, as an example, one can imagine living near a major roadway or factory. In this case, while the air pollution levels across the city may be tolerable, the concentrations affecting you locally will be higher and may not be tolerable if too high, since you live very close to an emission source, the road or factory. The first of the two lectures will cover these type of local air pollution issues in more depth. The second lecture topic, indoor air quality, relates to common types of air pollutants in the indoor environment, focusing on household sources, which of course vary individually and affect you more personally. The outline for this lecture comprises two topics. We first more clearly define and describe local air pollution by comparing it to ambient air pollution, which we have primarily focused on in previous course modules. We then study a class of air pollutants called air toxics. These are independent of criteria air pollutants and a class of air pollutants particularly important with respect to local air quality issues. Local versus ambient air pollution. The focus of previous course modules has been on what is termed ambient air pollution. The photographs below were shown earlier in the course when defining this. The one on the left overlooks an ambient air pollution layer over San Jose, while the one on the right shows a photochemical smog layer over Los Angeles. To review, the key points about ambient air pollution are as follows. First, it refers to outdoor air that spans broad areas. This can be seen from the photographs below, the air pollution spanning the city. Second, as such, it is relevant for general population exposure irrespective of individuals or specific neighborhoods. Third, concentrations can gradually spatially change over the city or city metropolitan area. However, this change is gradual and takes place over relatively large distance scales, say over tens of kilometers. Fourth, ambient air pollution is the result of the total combination of the many emission sources across the city, rather than any one source specifically. For example, ground level ozone, an important ambient air pollutant, is the result of citywide emissions of NOx, nitrogen oxides, and volatile organic compounds, VOCs, as we learned in Lecture 7. Lecture 8, take that back. These emissions are the collective result of the many mobile and industrial emission sources within the city. The slide below was shown in our previous lecture on ground level ozone. It shows the number of days of 8-hour average ozone standard exceedances across the Los Angeles basin. We learned that much of the poor ozone air quality in Los Angeles, and hence exceedances of the 8-hour air quality standard, occur over the eastern LA basin. This is depicted on the graphic, with over 80 days of exceedances at the most impacted areas in the Eastern Basin and much less days, 20 or less, in the Western Basin. This illustrates a key point from the previous slide that ambient air quality can change from place to place across the city, but changes are gradual over large distances. In this case, the distance scale between the least and most affected locations in the LA Basin is around 100 kilometers, quite a large distance in comparison to local air quality variations that we will cover shortly. In the northwestern LA area, within the San Fernando Valley, one also sees a higher exceedances in ozone levels, yet even here the higher levels span fairly uniform across the valley. With this review of ambient air pollution, we can now proceed to distinguish this from local scale air pollution. As mentioned in the introductory slides, we are concerned in this case with air pollution affecting more individually or at neighborhood scale. Because of this more local nature, air quality is more affected by emissions from specific sources. Two examples are shown in the photographs below. The one on the left is of the Geneva steel mill in Utah. You may recall this steel mill being mentioned when viewing the Arden Pope video on PM 2.5 health effects as part of one of your writing assignments. It was a large steel mill in Utah that was the primary emission source in the area. A strike caused the shutdown of the facility, after which air quality improved. This is an example of a major industrial source that would strongly affect air pollution for those living close by. The photograph on the right is of the Port of Oakland, which is a major local air pollution source due to the abundant ship and truck traffic into and out of the port. We learned that trucks emit diesel particulate, a particularly harmful type of combustion fine particulate. Ships also use bunker fuel, a heavy hydrocarbon fuel prone to air pollution emissions. There is much local concern in the community of West Oakland, within a couple miles of the port, about locally high air pollution disproportionately affecting citizens of the neighborhood. We can now summarize key points distinguishing local air pollution from ambient air pollution. First, it concerns exposure to individuals or specific neighborhoods, generally residing near a specific source or sources of emissions. Second, whereas ambient air pollution concentrations change very gradually over large distances, local air pollution concentrations decrease very strongly with distance from the specific emission source or sources in question. This is due to the dispersion or dilution of air pollutants as they travel downwind. Generally, appreciable changes in air pollution concentration in this case occur on the scale of hundreds of meters, out to say around several kilometers, let's say, much smaller than the distances of tens to 100 kilometers or larger, affecting ambient air pollution. Third, local air pollution generally involves specific local emission sources. Some important examples of local sources are here listed, which include major industrial complexes, oil refineries, ports, railways, and major roadways. Local air pollution problems are encapsulated with this graphic of air pollution hazards locally in the West Oakland area. Looking at the graphic, we see a map of the Oakland area. Notice first the scale of the map, around 8 kilometers by 8 kilometers, or 5 by 5 miles. We are therefore looking at neighborhood scale, rather than the entire city scale as in the LA Basin ozone exceedant graphic showed earlier. The Port of Oakland is on the lower left of the graphic, depicted by the ships lining the port entrance. The neighborhood of West Oakland is immediately across the Interstate 880 freeway east of the port by a mile or so. The map is color shaded according to distances from the source and locations downwind of the freeways based on typical local winds. The darkest colors, dark orange and lighter orange, indicate the most hazardous areas, within 2 miles of the port and downwind of the freeway. That's the darker orange here, lining the freeways. The lighter orange is the area within 2 miles of the port, regardless of proximity to freeways. The beige-colored areas are as the orange, but within 5 miles of the port. Although the air pollution concentrations are not depicted on this slide, the graphic illustrates main points of local air quality issues, that the distance scales are short on the scale of individual neighborhoods within a few kilometers or miles from the source, and that individual sources and distance from these sources are the key considerations when determining air pollution concentration impacts. We now highlight air quality concentration patterns from local sources more directly. In this graphic, we show a simple illustration of a plume of air pollution emitted from a single source for a single hour. The source is depicted by the black X on the graphic. The base map shows a city area of approximately 10 kilometers on a side. The shadings on the map depict concentrations of air pollutants emitted from the source over the hour, with different shading colors indicating varying ranges of concentrations, decreasing with distance from the source, from higher values in orange, near the source, to lower values in blue, further away from the source. Further annotating this graphic, we can depict the wind direction, which in this case, for the single hour depicted, is from the southwest. The wind direction dictates the direction of the plume, which blows downwind of the source from southwest to northeast. The different color shadings then correspond to ever-decreasing concentrations with distance from the source. Near the source, for example, the yellowish-green contour may signify the 50 ppm level. Areas within this contour line, therefore, are areas where the pollution concentration from the source for this hour are greater than 50 parts per million. Going further downwind, we can then denote the lower concentration contours. For example, the 20 ppm contour, the 10 ppm contour, the 5 ppm contour, and the 1 ppm contour. To explain more precisely, the area between the 10 and the 20 ppm contours, for example, are areas where the concentrations due to the source emissions for the hour are between 10 and 20 ppm. The total area enclosed by the 10 ppm contour, including the green and orange contours close to the source, is then the area where the concentrations are greater than 10 parts per million. These types of visuals, assuming the information is available to calculate a concentration field to construct it, can then be used to infer where concentrations are above or below a level of concern for adverse health outcome or other adverse health effects. For example, imagine the pollution plume in this visual corresponds to an accidental release of the pollutant hydrogen chloride from some industrial facility. The industrial facility is shown by the X. Perhaps the accident resulted from a rupture of a liquid chlorine tank or pipeline, spilling the chlorine, which in turn rapidly volatilizes into a toxic gas cloud of hydrogen chloride that blows downwind, affecting the neighboring community. From previous health studies, it is determined that the concentration level for a 1-hour inhalation exposure to hydrogen chloride, at which serious, lasting health problems can result, is around 20 parts per million. This comes from the Acute Exposure Guideline Levels, or EAGLES, which give levels of concern for acute exposure for inhalation of various chemicals. Web links to learn further details about Eagle standards are provided here for those interested. Notwithstanding, given 20 ppm as a level of concern for a 1-hour exposure, the area encompassed by the 20 ppm contour is therefore that where 1-hour average concentrations are greater than 20 ppm due to the release. This is therefore the area where serious lasting health impacts may be anticipated due to the accident, since the level of concern is 20 parts per million. Contrarily, areas beyond the 20 part per million contour are those where concentrations are less than 20 ppm, and therefore impacts may be irritating but not as serious or long-lasting. Emergency responders can use this information to prioritize evacuations due to the accident or to take other preventative measures. These types of contour maps are also commonly used in civil litigations, which often result after major environmental accidents in efforts to settle claims. The graphic below is similar to that just shown, but this time depicting the average concentration of plumes from an emitting source over a year. This would be important for, say, chronic exposure, since in this case we are interested not in a particular hour, but average exposure over a year due to emissions from the source. The layout of the graphic is as before, with the source indicated by the X and contours of decreasing concentrations emanating from the source outward with distance from the source. In the case of this graphic, the concentration levels corresponding to the graphics are indicated by a legend on the lower right, with orange indicating 6,000 micrograms per meter cubed, green 1,000 micrograms per meter cubed, and purple 100 micrograms per meter cubed. The main distinction, however, is that instead of this graphic being for a single hour, it depicts the average concentration field over a year. Therefore, we do not have a single hour wind in a single direction as we had shown previously, but instead a windrows of the wind frequencies depending on direction over the year. We learned about windrows in Lecture 7. The student is referred back to this for review. Looking at the windrows, it is seen that most of the winds are from two directions, from the north and from the southwest sectors. This helps explain the shape of the pollution contour field. Since there is a high frequency of winds from the north, the average pollution field can be seen to protrude more so to the south compared to other directions, since plumes from the source blow from the north to south relatively more frequently due to the higher frequency of north winds. There is also a protrusion of the plume pattern to the northeast, based on the relatively higher frequency of winds from the southwest, which blow plumes from the source to the northeast. Windroses are therefore very useful tools to determine directions from emission sources where local impacts due to continuous emissions from the source may be most pronounced. Air toxics. So far, the course has focused on criteria air pollutants, the 7 pollutants that have ambient air quality standards and are therefore designed to be protective of ambient air quality. We now cover another class called air toxics, which tend to be relatively important for local scale air pollution issues since their emissions are often more due to specific isolated sources and therefore affect more so communities living near these sources. Air toxics consist of many species. We'll see a listing of some of these shortly. Most air toxics are carcinogenic, and therefore the most important health risk due to inhalation of air toxics is increased risk of cancer. A couple of synonyms for air toxics are hazardous air pollutants, or HAPs, and toxic air contaminants, or TACs. The following is a list of some of the common air toxics. As you can see, these consist of various esoteric species. However, they can be summarized within certain groups that may be more familiar. The first are various species that are volatile organic compounds, or VOCs. For example, benzene, 1,3-butadiene, formaldehyde, vinyl chloride, and others. We learned about VOCs earlier in the course in the context of VOCs being ozone precursors. But many VOCs are also air toxics, potentially harmful directly due to their carcinogenic nature. Certain air pollutant species therefore have multiple adverse health effects that must be considered. A second group of air toxics is metals. For example, cadmium, hexavalent chromium, arsenic, lead, and nickel. These are among the fine particulate class, but specific to species that consist chemically of metals. Of these, hexavalent chromium, or chromium in the 6th rather than the more common 3rd valence stage, is especially harmful. There are also several air toxics that are complex carbon particulate species. For example, benzopyrenes, dioxins, and diesel particulate. These tend to be emitted from combustion of heavy hydrocarbon fuels. We had previously mentioned diesel particulate as especially harmful in our lecture on particulate air pollution in course module 3. A summary of these main classes of air toxics is provided here. Most air quality districts in California have active programs to reduce exposure to air toxics. Among the most complete citywide assessments with respect to air toxics exposure is the Multiple Air Toxic Exposure Studies, or MATE studies, over the Los Angeles Basin, conducted by the South Coast Air Quality Management District. Intensive measurements and modeling analyses of air toxics across the city are carried out in this study every 5 years or so and summarized in reports. Among the main goals of the MATE studies is to assess the distributions of air toxic concentrations across the city in order to identify areas of the city and neighborhoods affected most predominantly by air toxics. The most recent MATES study is MATES 4, from July 2012 to June 2013. Since the main inhalation risk due to air toxics is cancer, a central result of the MATES studies is the generation of maps depicting estimates of the increased cancer risk due to inhalation of air toxics across the basin. The map shown here is for all air pollutants combined and expresses the increased risk of cancer above baseline due to inhalation of air toxics at different locations across the LA basin in number of increased cancers per million people. Peak increased risks are depicted by the dark purple, indicating increased risks of about 1,000 extra cancers per million people above baseline. Lighter purples are about 500 extra cancers per million above baseline. Yellows are lower values. The underlying concentration field of air toxics used to calculate the risks on this map is based on measurements and modeling carried out by the MATES studies. The risks depicted on this map assume a 70-year or lifetime exposure to the underlying estimated air toxic concentrations. Looking at the map, the main point that can be seen is the local nature of the risks. One can see, for example, higher cancer risks in locations corresponding to many of the types of local sources mentioned earlier. For example, higher risks is seen over the Port of Los Angeles, the Los Angeles LAX airport, near sections of major freeways and near industrial areas and corridors. This is because air toxic exposure tends to be more localized due to specific sources compared with typical ambient air pollutants such as ozone, nitrogen dioxide, and PM 2.5. From an exposure point of view, cancer risk due to air toxics is therefore more dependent on proximity to these major emission sources. Air districts are also required to manage risk of toxic air contaminant exposure from single emitting facilities through the California AB 2588 Toxics Hotspots legislation. Seen here is an example of such an analysis from some industrial facility. The facility outline is shown in black. Facilities are required to calculate increased risks of various adverse health effects due to exposure to air toxics concentrations resulting from their air toxics emissions. Since cancer risk is generally the main effect, we focus on the red outline, which is the contour where average annual concentrations of all toxics combined emitted from the facility are sufficiently high in concentration to produce a greater than 10 in a million increased risk of cancer for someone exposed long term to these concentrations. The AB 2588 regulation requires public notification of the increased risk for those within the 10 in a million contour. Therefore, in this case, notification would be required for those living within the red contour. The other contours shown, yellow and orange, refer to other requirements aside from cancer risk, which we will not cover.